frozen world just turned up at the edge of our solar system, 66 times farther from the sun than Earth, silent, drifting, and it just broke our best theory about Planet 9. Scientists found it. They ran the simulations, and the math says a hidden giant planet either got violently thrown out of our solar system billions of years ago, or it is still out there right now, invisible and enormous, 5 to 10 times heavier than Earth. Two separate teams, two opposite answers, both confirmed by real data. We will track the frozen fossil called ammonite, follow the heat signatures hiding in deep space, and find out what is really lurking at the edge of everything we know. If you enjoy this journey, hit like and subscribe. It genuinely helps. Prepare yourselves. We begin. You learned 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Clean, ordered, done. That map is wrong. Astronomers have been quietly building a case for years. A case that says something enormous is hiding in the dark beyond Neptune. Something so far out that sunlight barely reaches it. Something that has been pulling on the outer solar system this entire time without anyone seeing it. And the evidence keeps piling up. Here is the problem. The outermost planets and the frozen objects beyond them do not orbit the sun the way they should. Their paths tilt. They cluster. They stretch toward the same region of space, like they are all being tugged by the same invisible hand. Scientists ran the numbers in 2016 and published a paper that shook the astronomy world. The gravitational math pointed to one conclusion: a hidden planet, a giant one, sitting somewhere between 400 and 800 times the distance from Earth to the Sunday. To picture that distance, imagine the sun as a basketball sitting in the middle of a football field. Earth is a tiny pebble about 30 feet away. Planet 9, if it exists, sits somewhere around 2 miles outside the stadium, in total darkness, never seen, never confirmed, but mathematically demanded. That is the theory, and for years it held together beautifully. Then something new showed up. In 2023, a telescope in Hawaii caught a faint light moving through the deep outer solar system. Astronomers tracked it, measured it, and realized they had found something rare, an object so far from the sun, so detached from every planet's gravity, that it belonged to a class of worlds so unusual that only 3 others like it had ever been discovered in human history. They called it ammonite. And ammonite had a problem. Its orbit did not match the prediction. The path it traveled through space pointed in the wrong direction. Every computer model said that if Planet 9 existed where scientists thought it did, ammonite should have been flung out of the solar system billions of years ago. The planet's gravity would have grabbed it and thrown it into interstellar space like a slingshot. But ammonite is still here, drifting, stable, perfectly preserved. So either Planet 9 is somewhere completely different from where every model placed it, or something far stranger happened in the ancient past. A violence so massive it rearranged the entire outer solar system and left ammonite as the only witness. At the exact same time, on the other side of the world, a different team of researchers was running a completely separate experiment. They were searching for Planet 9 using heat instead of light, and they found 2 objects sitting right where Planet 9 was supposed to be. 2 faint glowing shapes, barely moving, exactly the right temperature for a giant hidden planet. 2 teams, 2 experiments, 2 answers that point in opposite directions. One says, Planet 9 is gone, ejected, a rogue drifting through the Milky Way in permanent darkness. The other says it is right there, waiting. Both results come from real data, real telescopes, and real peer-reviewed science. So which one is right? To answer that, you have to understand what ammonite actually is, because this frozen world hiding at the edge of everything is unlike anything else we have ever found. And the story of how it got there goes back to the most chaotic period in our solar system's history. Most space objects play by the rules. Asteroids orbit in a belt between Mars and Jupiter. Comets swing in from far out, loop around the sun, and head back. Even Pluto, sitting billions of miles away, still feels Neptune's gravity, still responds to the pull of the planets, still belongs to the neighborhood. Sednoids do not belong. They are a class of objects so far removed from every planet in the solar system that nothing out here touches them. No planet pulls on them. No gravitational handshake connects them to Neptune or Uranus or anyone else. They float in a zone of total gravitational silence, following orbits so enormous that one lap around the sun takes thousands of years. To picture it, imagine you live in a city. The city has roads, traffic, people bumping into each other, forces pushing and pulling everyone in every direction. Asteroids and comets live in the city. Sednoids live so far outside the city that they cannot even see the lights from it. They exist in a completely different gravitational world. That is what makes them impossible to explain with our current models. Every other object in the solar system ended up where it is because something pushed it there. A planet's gravity, a collision, a slow drift over millions of years caused by the combined pull of the gas giants. Scientists can trace the history of almost anything in the solar system back to a physical cause. Sednoids break that chain. Their orbits are so wide, so stretched, so impossibly far from any planetary influence that nothing in the current solar system could have put them there. Something had to do it. Some enormous force had to have grabbed these worlds and flung them into these extreme paths billions of years ago. And whatever that force was, it left almost no other trace behind. The first Sednoid ever found was Sedna, discovered in 2003. Astronomers stared at the data for years trying to explain how Sedna got its orbit. They could not. No combination of known planets, no gravitational trick from Neptune, nothing in the standard model of the solar system produced an orbit like Sedna's. So scientists started entertaining bigger ideas. A passing star billions of years ago, a dense cluster of stars the early sun traveled through before escaping into open space, or a giant hidden planet still orbiting today, whose gravity stretched these objects into their extreme paths. Then a second Sednoid turned up, then a third, each one with its own impossible orbit, each one adding pressure to the question of what put them there. Then Ammonite became the fourth. But here is what makes Ammonite different from the other three. The first three Sednoids all orbit in roughly the same region of the sky. Their paths cluster together. That clustering is actually one of the main pieces of evidence scientists use to argue for Planet 9. The theory says a hidden giant planet herded them into alignment with its gravity, the way a magnet organizes iron filings. Ammonite orbits in a completely different direction. It refuses to line up. Its path cuts across the pattern, and that single fact threatens to collapse years of careful mathematical work. Something extraordinary is coming, because the story of how Ammonite was actually spotted involves a telescope, 3 years of patient skywatching, and a discovery that nobody fully expected. Finding a Sednoid is harder than finding a single grain of sand on a dark beach at midnight. These objects are frozen. They reflect almost no sunlight. They sit so far from the sun that even the best telescopes on Earth barely catch a glimmer. To find one, you have to scan enormous patches of sky, night after night, looking for something so faint it nearly disappears into the background noise of the universe. That is exactly what a team of astronomers set out to do using the Subaru telescope, a massive instrument sitting near the summit of Mauna Kea in Hawaii at an altitude of almost 14,000 feet. Up there, above most of the atmosphere, the sky is dark and clear in a way that most people never experience. In March 2023, the telescope captured the first images of what would later become known as Ammonite. The official name, 2023 KQ14, tells you the year and the order of discovery. But Ammonite is the name that stuck. They also observed it again in May and August of that same year, tracking its movement across the sky with extraordinary precision. Here is the problem with finding objects this distant. They move incredibly slowly. A rock in the asteroid belt moves fast enough that even amateur telescopes can track it over a single night. Ammonite, sitting 66 times farther from the sun than Earth, barely shifts at all. Night after night, it looks almost completely stationary. Only by comparing images taken weeks or months apart can astronomers detect the tiny crawl that reveals an object is actually moving through our solar system, and not just a background star. That slow drift is both the obstacle and the proof. To confirm the discovery, the team needed a second telescope. In July 2024, over a year after the first sightings, the Canada-France-Hawaii telescope captured its own observations of Ammonite and verified the detection. 2 independent instruments, 2 separate teams. Same result, Ammonite was real. Now comes the measurement that changes everything. Once scientists had enough data points, they calculated Ammonite's orbit with precision. They found its perihelion, the closest point it ever comes to the Sun during its enormous loop through space. That distance came out to 66 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. 66 times, that puts Ammonite at over 6 billion miles from the Sun at its closest approach. To feel that scale, light travels from the Sun to Earth in about 8 minutes. Light from the Sun takes over 9 hours to reach Ammonite at its closest point. At its farthest, the journey would take far longer. And yet, Ammonite keeps orbiting, slowly, silently, completing 1 full trip around the Sun in a time frame so vast that human civilization has existed for only a tiny fraction of a single Ammonite year. The team published their findings in Nature Astronomy in July 2025. The paper confirmed every measurement, and buried inside the data was the orbit that broke the Planet 9 models. Something about this orbit was deeply wrong, and the closer scientists looked, the more unsettling it became. 66 times farther from the Sun than Earth. Say that number out loud, and it sounds like a lot. But numbers alone do not communicate what that distance actually means for a physical object trying to survive in space. At Earth's distance, the Sun is bright enough to burn your skin in minutes. Its gravity holds us in a tight, reliable orbit. Its warmth keeps liquid water on the surface. The Sun is everywhere in our experience of the solar system. At 66 times that distance, the Sun shrinks to a bright star, barely distinguishable from the other stars in the sky. Its warmth drops to almost nothing. Temperatures on Ammonite hover around -400 degrees Fahrenheit. The surface is frozen so completely that the ice there has not changed in billions of years. But the distance does more than just make Ammonite cold. It places Ammonite in a gravitational dead zone that should be impossible to explain with our current models of how the solar system formed. Here is why. Every object in the solar system got its orbit from something. Early in the solar system's history, the giant planets, Jupiter, Saturn, Uranus, and Neptune, were moving around. Their gravity scattered smaller objects constantly. Some got flung inward, some got flung outward, some were kicked into the inner solar system and eventually crashed into planets or the Sunday. Others were thrown so far out they joined the Oort cloud, a vast shell of frozen material sitting trillions of miles away. But the objects that ended up in the middle ground, too far from Neptune's gravity to be influenced by it, and too close to the Oort cloud to have been pushed there by a passing star, should not exist. There is no known mechanism in standard planetary science that puts an object in Ammonite's orbit. Think of it like throwing a ball onto a rooftop. You can throw it hard enough to clear the building entirely. You can toss it gently, so it bounces back. But landing it precisely on the roof, with no run-up, no bounce, no second try, that requires a force you cannot see acting exactly at the right moment. Something placed Ammonite there deliberately, in the sense that physics demanded a specific cause. The 3 most likely explanations are a passing star that brushed through the outer solar system billions of years ago and scattered objects into extreme orbits, the gravitational pull of a dense star cluster the early Sun traveled through before escaping into open space, or a massive hidden planet still orbiting today. pulling objects into these remote paths with its enormous gravity. Each explanation has evidence for it. Each has problems too. But here is the part that scientists find most disturbing. Ammonite's orbit has been stable for 4.5 billion years. The simulations confirm this. Whatever force put it there did so with enough precision that Ammonite has been circling the Sun in the same path since the solar system was brand new. That kind of stability requires an explanation. And the leading explanation, Planet 9, just ran into a serious obstacle. Because the same computer models that show Ammonite surviving for billions of years also show that Planet 9, sitting where scientists thought it was, would have destroyed that stability long ago. Every planet in our solar system is connected to everything else. Neptune pulls on the Kuiper belt. Jupiter's gravity shapes the asteroid belt. Even tiny Pluto feels the tug of Neptune and adjusts its path in response. The solar system is a web of gravitational relationships, each object leaning slightly toward everything else, the whole system balanced in a constant slow dance. Sednoids stepped off the dance floor. Their orbits sit in a zone where no planet's gravity reaches them. Neptune, the outermost confirmed planet, exerts gravitational influence out to roughly 30 astronomical units from the Sunday. Ammonite's closest approach is 66 astronomical units. Even at its nearest point, it sits more than twice as far from Neptune's reach as Neptune is from Earth. In practical terms, this means nobody is pushing Ammonite around. When Earth wobbles slightly, Jupiter is responsible. When comets get nudged out of the Oort cloud and fall toward the Sun, a passing star or the gentle pressure of the galaxy itself is the culprit. Every object in the solar system has a gravitational story. Something moved it. Something shaped its path. Something is still touching it right now. Ammonite has no current gravitational story. Its orbit is so stable, so perfectly preserved, that scientists can run simulations forward and backward for billions of years, and Ammonite stays exactly where it is. No planet is nudging it. No force is slowly reshaping its path. It just circles, endlessly, alone. That isolation is what makes sednoids scientifically valuable, because an object that nothing is currently touching is like a crime scene that has never been disturbed. Whatever happened to Ammonite billions of years ago is still written into its orbit, frozen in place, waiting to be read. Scientists are trying to read it right now, and the reading is alarming. Here is what the orbit says. At some point in the ancient past, a force enormous enough to move a world grabbed Ammonite and stretched its path into this extreme shape. That force had to be gravitational. Gravity is the only thing that works on objects this large at these distances. So something with enormous mass was in this region of space, either passing through or orbiting, and it sculpted Ammonite's path before vanishing or moving on. The 4 sednoids discovered so far all have orbits shaped by similar extreme forces. All 4 sit in that same gravitational dead zone. All 4 preserve the memory of a violent ancient event that standard planetary science cannot fully explain. 3 of them cluster in a similar region of the sky. That clustering screams Planet 9, because a massive orbiting planet would naturally herd objects into the same gravitational neighborhood over billions of years, the same way ocean currents naturally sweep debris into the same patches of water. Ammonite refuses to cluster. It points a different direction, and that one fact is forcing scientists to ask a question nobody wanted to ask. What if the clustering of the other 3 sednoids is a coincidence? What if there are only 4 of these objects, because we can barely find them at all, and the real picture, with hundreds or thousands of sednoids in every direction, would show a completely different story? The answer to that question changes everything about what we think happened 4.5 billion years ago. And the next discovery sharpens the mystery further. 4 objects. That is the entire known population of sednoids in the solar system. 4 worlds in 4.5 billion years of solar system history. 4 frozen records of something ancient and violent, and every single one of them forces scientists to update their models. The first was Sedna, found in 2003 by a team scanning the sky with a telescope in California. Sedna sits even farther out than Ammonite, with a closest approach to the Sun of about 76 astronomical units. Its orbit is so enormous that one full trip around the Sun takes roughly 11,000 years. When Sedna was discovered, astronomers genuinely had no good explanation for it. Nothing in the standard model of solar system formation produced a Sedna. It was an anomaly, a ghost object sitting where no ghost should be. Scientists spent years debating what created Sedna's orbit. Some suggested a passing star. Some pointed to the star cluster the young Sun may have traveled through. A few proposed a hidden planet, but without other examples to compare it to. The debate stayed theoretical. Then a second sednoid appeared, designated 2012 VP 113 and nicknamed Biden by some in the astronomy community. This object has a closest approach of about 80 astronomical units. Finding a second sednoid in roughly the same region of the sky as Sedna gave the hidden planet theory a huge boost. A coincidence with two data points starts looking like a pattern. The third sednoid, designated 2021 RR205, pushed the pattern further. 3 objects, 3 extreme orbits, all roughly clustering in the same broad direction of the sky. The Planet 9 models strengthened with each discovery. If a hidden planet was herding these objects gravitationally, 3 clustered sednoids made perfect sense. Each new discovery tightened the mathematical case. Each one seemed to confirm that something enormous was out there, invisible but gravitationally active, sculpting the outer solar system from a distance. Then Ammonite arrived, the 4th sednoid, the one that breaks the pattern. Its orbit does not cluster with the others. It points a different direction. And for a hypothesis that relies on clustering as its main evidence, a 4th sednoid pointing the wrong way is a serious blow. Here is why the math gets complicated. When you have 3 data points all pointing the same direction, the odds of that being random chance are low. Scientists calculated those odds and concluded that the clustering of the first 3 sednoids was statistically unlikely to be accidental. Planet 9 seemed like the only reasonable explanation, but when the 4th data point points in a completely different direction, the question of sample size becomes uncomfortable. Maybe 3 clustered sednoids out of 4 total are not enough to draw a confident conclusion. Maybe we are looking at 4 objects out of hundreds or thousands that exist throughout the outer solar system in all directions, and we just happen to find 3 that clustered first. Or maybe the clustering is real, and Ammonite is a special case, an object that escaped Planet 9's gravitational herding for reasons the models have not captured yet. The researchers who discovered Ammonite ran simulations specifically to test this. What they found did not simplify anything. The computer runs for hours. Millions of virtual years pass in minutes. This is how astronomers test planetary theories. They build a model of the solar system inside a computer, plug in the known planets, add a hypothetical Planet 9 at its predicted location and mass, and then watch what happens to every object in the outer solar system over billions of simulated years. When scientists ran Ammonite through these models, the results were direct. Planet 9, sitting at the location and distance most models predicted, would have interacted with Ammonite at some point during the last 4.5 billion years. The gravity of a planet 5 to 10 times heavier than Earth, sitting hundreds of astronomical units away, would have reached out and disturbed Ammonite's orbit. The simulation showed the most likely outcome clearly. Ammonite would have been kicked out of the solar system entirely, sent flying into interstellar space on a one-way trip that never ends. But Ammonite is still here. Its orbit is stable. It has been stable for the entire history of the solar system. That means one of 3 things happened. Option 1, Planet 9 does not exist. The clustering of the other sednoids is a statistical accident, and there is no hidden planet at all. The strange orbits of sednoids came from some other ancient force, a passing star, an early star cluster, or a mechanism science has not identified yet. Option 2. Planet 9 exists, but it sits far beyond where scientists thought, so far out that its gravity barely reached Ammonite. This means Planet 9 is even more distant, even colder, even harder to find than the already extreme predictions. Option 3. Planet 9 used to exist. A giant planet formed in the outer solar system billions of years ago, stirred up the sednoids with its enormous gravity during a chaotic period, then got gravitationally destabilized and ejected into interstellar space. Ammonite survived that ancient catastrophe and settled into its current stable orbit after the planet left. Yukun Huang, the lead researcher on the Ammonite study at the National Astronomical Observatory of Japan, stated publicly that this discovery significantly lowers the probability of the standard Planet 9 hypothesis. Significantly, that word carries weight in science. It means the math changed. The third option, the ejection scenario, is the one that gives astronomers genuine unease. Because if true, it means a planet the size of Neptune once orbited our Sun and is now wandering the galaxy in total darkness, too cold, and too far from any star to be visible with any instrument currently in existence. A rogue planet, ejected from our own solar system, carrying ancient gravitational scars from the neighborhood it was thrown out of. And Ammonite, sitting alone in its frozen orbit, 66 astronomical units from the Sun, is the best evidence that something catastrophic happened here long ago. The story of what that catastrophe may have looked like is far more violent than most people expect. Scientists trust simulations the way engineers trust blueprints. You cannot wait 4.5 billion years to watch a solar system evolve in real time. So astronomers build the solar system inside a computer, accurate down to the gravitational pull of every known major object, and then run it forward through virtual time. The math is well understood. Gravity follows precise rules, and if the model is built correctly, it will show you what happened in the ancient past as clearly as a recording. The team that discovered Ammonite ran exactly these simulations after measuring its orbit. They placed the known planets in their correct positions. They added the other 3 sednoids. They added Ammonite, and then they added Planet 9, a world between 5 and 10 Earth masses, orbiting somewhere between 400 and 800 astronomical units from the Sun, exactly where most theoretical models place it. Then they hit play. Over billions of simulated years, Planet 9's gravity reached across enormous distances and began touching the sednoids. The 3 clustered ones, Sedna and the others, responded in a way that matched Planet 9's predictions. Their orbits shifted. They clustered more tightly. The model confirmed what scientists had already suspected. A massive planet in that region would naturally herd those 3 objects together. But Ammonite moved differently. Its orbit, angled away from the others, put it in a gravitational relationship with the simulated Planet 9 that ended badly. Over the course of billions of simulated years, Planet 9's gravity tugged on Ammonite at each close approach, and each tug bent the orbit slightly further, slightly less stable, slightly more vulnerable. The cumulative effect was ejection. Virtual Ammonite left the solar system, accelerated outward, and never came back. Real Ammonite is still here. That gap between the simulation and reality is the scientific crisis at the center of this story. The model, using the best available understanding of Planet 9's location and mass, produces a solar system without Ammonite. The real solar system has Ammonite. Something in the model is wrong. The most straightforward fix is to move Planet 9 farther out, push it to a distance so extreme that its gravity could not have reached Ammonite powerfully enough to eject it. But moving it farther creates new problems. A more distant Planet 9 becomes even harder to detect. The heat it radiates drops further. The reflected sunlight, already almost non-existent, dims even more. And a farther planet means the gravitational herding that explained the clustering of the first 3 sednoids becomes weaker, which requires new explanations for why those 3 still cluster. Every fix creates a new complication. The other fix, the one that some scientists find more compelling with each passing discovery, is to remove Planet 9 from the model entirely and replace it with a past catastrophe. A planet that once existed, did its gravitational work, and then left. This is the ejection scenario. And it is far more dramatic than it sounds. Because if a giant planet was ejected from our solar system, the event that caused that ejection would have been one of the most violent things that ever happened in our cosmic neighborhood. It would have left marks everywhere, and we may have been living inside those marks all along without knowing it. 4.5 billion years ago, the solar system looked nothing like it does today. The sun was young, the planets were still forming, crashing into each other, growing, shifting orbits. Jupiter and Saturn were not sitting where they sit now. The outer solar system was a chaotic construction zone, planets migrating inward and outward, their gravitational pulls reshaping everything they touched. Scientists call this period the Late Heavy Bombardment Era, a time when massive collisions were common, when entire planetary bodies could form, wander, and be destroyed in the span of a few 100 million years. This is the setting for the ejection scenario. The theory goes like this. An additional giant planet formed in the outer solar system during this violent early period. This planet, roughly the size of Neptune or larger, settled into an orbit somewhere beyond the gas giants. It began gravitationally interacting with the sednoids, pulling them into extreme orbits, stretching their paths into the distant frozen zone where they still sit today. But the young solar system was unstable. The giant planets were still migrating. Jupiter, the largest planet, was moving through the outer solar system and reshaping every gravitational relationship it touched. Saturn, Uranus, and Neptune were doing the same thing on a smaller scale. At some point, this additional giant planet had a close encounter with one of the established gas giants. The gravitational exchange was catastrophic. Like two massive billiard balls colliding at high speed, the encounter transferred enormous amounts of energy in an instant. One planet gained velocity, the other slowed slightly. The one that gained velocity gained enough to escape the sun's gravity entirely. It became a rogue, moving faster than escape velocity. This world left the solar system on a trajectory that would carry it outward forever, past the farthest edges of the Oort cloud, past the point where the sun's gravity could hold anything, into the open darkness of interstellar space. The remaining solar system settled. The surviving planets found their current orbits. The sednoids, already pushed into their extreme paths by the ejected planet's gravity, froze in place. And the scars of that ancient violence became permanent features of the outer solar system. Ammonite, under this theory, is one of those scars. Its orbit preserves the memory of what happened before the giant planet left, a gravitational fossil, locked in a path shaped by something that no longer exists. This scenario is a theory. Scientists have confirmed the chaotic migration of the early solar system. They have confirmed that giant planet ejections happen. Astronomers have found rogue planets drifting through the galaxy, worlds wandering without stars, surviving in total darkness. The ejection of a planet from our own solar system is physically plausible. What remains unknown is whether it actually happened here. But if it did, that ejected world is out there right now, moving through the Milky Way, cold, dark, alone, and almost completely impossible to find. Imagine a planet with no sun, a world roughly the size of Neptune, with a surface of frozen gas and ice, drifting through the galaxy at thousands of miles per second. No star warms it, no seasons mark its time, no light reflects off its surface toward any telescope in any direction. This is what a rogue planet looks like, and astronomers have already confirmed they exist throughout the galaxy. Scientists have found rogue planets by watching what happens when one drifts between Earth and a distant background star. The rogue's gravity bends the starlight, briefly brightening it in a way that reveals the presence of a massive object. This technique is called gravitational microlensing, and it has confirmed that free-floating planets are scattered throughout the Milky Way. Some estimates suggest there may be billions of them. The one that may have been ejected from our own solar system would be one of the most significant ever identified, if it could be found. but finding it presents a near impossible challenge. At the temperature of a rogue planet that formed in a solar system and then was ejected, the surface sits somewhere around -300 to -400 degrees Fahrenheit. That temperature does produce a tiny amount of infrared radiation, heat energy radiating away into space. But the amount is so small and the distances involved so enormous that current telescopes cannot detect it unless they know exactly where to look. And that is the problem. A rogue ejected from our solar system could be anywhere along its escape trajectory. It has had 4 billion years to travel, moving at even a fraction of the speeds measured in other ejection events. It could now sit tens of thousands of astronomical units away, or hundreds of thousands. The search area is essentially the entire galaxy. The James Webb Space Telescope has imaged rogue planets drifting through nearby star-forming regions. Young rogue planets, still warm from their formation, glow brightly enough to detect. An ancient cold one, ejected billions of years ago, generates almost no heat at all. So, if a ninth planet was thrown out of our solar system, we almost certainly cannot find it now. What we can do is find the evidence it left behind. The sednoids are that evidence, their impossible orbits, their gravitational isolation, their perfectly preserved paths through space. All of these carry the fingerprints of something massive that passed through long ago. But here is what sharpens the tension. While some scientists focus on the ejected planet theory, others are running a completely different kind of search. They believe Planet 9 is still here, still orbiting, still hiding in the dark far beyond Neptune, and they think they just found it. 2 heat signatures sitting in the exact region of the sky where Planet 9 should be. 2 faint glowing objects that move in exactly the way a distant giant planet should move. 2 candidates that fit every thermal prediction for a world 5 to 10 times heavier than Earth. The story of how they found it starts with a Japanese space telescope that most people have never heard of. The solar system you see now is the calm after a storm that lasted hundreds of millions of years. In the beginning, the sun formed from a collapsing cloud of gas and dust. The leftover material spread into a spinning disk surrounding the young star. Slowly, dust grains stuck together. Pebbles formed. Boulders appeared. And over millions of years, gravity gathered those boulders into planetesimals, which grew into the planets. But the early planets did not sit still. Jupiter formed first, faster than everything else, because it sat far enough from the sun that ice could form along with rock, giving it far more raw material to grow from. Jupiter became so large, so fast, that its gravity began reshaping the entire solar system. It pushed objects inward. It pulled objects outward. It sent swarms of ancient rocks crashing into the inner planets, an event scientists call the Late Heavy Bombardment that scarred Mercury, the Moon, and Mars with the impact craters we can still see today. Saturn formed next. Then Uranus and Neptune, though scientists now believe Neptune and Uranus may have formed in different positions than they currently occupy. Computer models suggest Uranus and Neptune both migrated outward over hundreds of millions of years, pushed by gravitational interactions with Jupiter and Saturn. This migration is not gentle. When a planet the size of Uranus moves outward by hundreds of millions of miles, every smaller object in its path gets scattered. Some get flung into the inner solar system, some get thrown into the Kuiper belt, some get pushed into the extreme outer solar system, into orbits so distant they become sednoids. Here is what makes this relevant to the Planet 9 story. If the early solar system was violent enough to move Uranus and Neptune from their original positions, it was absolutely violent enough to have hosted an additional giant planet, a world that formed in the chaos, moved with the migrations, and eventually found itself in a gravitational situation it could not survive. Scientists have run models where the early solar system contained 5 giant planets: Jupiter, Saturn, Uranus, Neptune, and one more. In many of those simulations, the 5th planet gets ejected. In some simulations, it is thrown out early. In others, it survives longer, shaping the outer solar system before its eventual escape. This is confirmed as a plausible scenario. Giant planet ejections happen in simulations of real solar systems, not just theoretical ones. Astronomers have observed other star systems in the galaxy, with debris patterns that strongly suggest past giant planet ejections. Our own solar system carries several features that planetary scientists find slightly awkward to explain with only 8 planets. The gap in planetary mass between Neptune and the inner solar system, the unusual structure of the Kuiper belt, which is far less dense than models predict, the orbits of the sednoids. Each of these is a small piece of a puzzle. And when you lay them all out together, a 5th planet, once present and later gone, becomes one of the tidiest solutions. But tidiness in science is not confirmation. The hunt continues. Think of Ammonite as a recorder that has been running since the solar system was born. Every object in the solar system carries gravitational memories. The shape of an orbit, its angle, its distance from the sun. All of these are determined by forces that acted on the object in the past. For most objects, those forces keep acting. Neptune is still nudging Pluto today. Jupiter is still sculpting the asteroid belt. The gravitational memories of inner solar system objects get overwritten constantly. Sednoids are different. Once they settled into their isolated orbits, the writing stopped. No planet touches them now. No force is reshaping their paths. Their orbital records have been sitting in perfect preservation since the very beginning, unchanged by 4.5 billion years of solar system history. Every feature of Ammonite's current orbit is a direct message from the ancient past. Scientists can read that message with mathematics. By calculating the gravitational forces required to create and maintain Ammonite's specific orbit, researchers can work backward in time. They can ask, what kind of force, at what distance, with what mass, had to act on this object at some point in the past to produce the orbit we see today? The answer narrows the possibilities dramatically. The force had to be gravitational. It had to be enormous. And it had to have acted during the early solar system, because Ammonite's orbit has been stable for 4.5 billion years, meaning the force that shaped it is either still acting today, or it acted powerfully in the ancient past and then disappeared. This is exactly the kind of detective work that makes sednoid science so powerful and so frustrating simultaneously. The evidence is clear. The crime definitely happened, but the suspect either fled or is hiding in such extreme darkness that our instruments cannot find it. What makes Ammonite specifically valuable is its difference from the other 3 sednoids. In forensic terms, if 3 witnesses all tell the same story, and a 4th witness tells a different one, scientists have to decide which is more informative. The 3 clustered sednoids could all have been influenced by the same force, Planet 9's gravity, which herded them into alignment. Ammonite was influenced by something different, or by the same force at a different time when it acted differently. One scenario scientists are exploring is that Ammonite was placed in its current orbit during the chaotic early migration period, before Planet 9 settled into its eventual orbit. The gravitational landscape of the early solar system changed rapidly. An object pushed into an extreme orbit during the peak chaos would look different from objects pushed in later when the system had partially stabilized. Another scenario holds that Ammonite's orbit came from something entirely different. A passing star's brief gravitational influence 4 billion years ago, which barely grazed the outer solar system and flung Ammonite into its current path. Both scenarios are live options, and neither requires Planet 9 to currently exist. That is the uncomfortable truth at the center of this story. The evidence cuts both ways, and the search for clarity led 2 different teams to 2 completely different methods and 2 completely different results. Science rarely moves in a straight line. While Yukun Huang and his team in Japan were analyzing Ammonite's orbit and running the simulations that challenged the Planet 9 hypothesis, another researcher on the other side of the planet was doing the opposite, building the strongest case for Planet 9's existence using data no one had ever applied to this problem before. Amos Chen, a researcher at National Tsinghua University in Taiwan, looked at the Ammonite problem from a completely different angle. The orbit-based evidence was getting messy. The clustering debate was unresolved. The simulations produced contradictory results depending on where you placed Planet 9. Chen decided to stop arguing about gravitational clues and look for the planet directly. The challenge with direct detection is enormous. Planet 9, if it exists, sits somewhere between 400 and 800 astronomical units from the Sunday. At that distance, reflected sunlight is essentially useless. The sun's light, already faint by the time it reaches Neptune, weakens massively over the additional hundreds of astronomical units to Planet 9's predicted location. The reflected glow off a planet that distant would be invisible to every standard optical telescope currently operating. Chen's team approached the problem differently. Every planet generates its own internal heat. Jupiter radiates more energy than it receives from the Sunday. Saturn does the same. Even Uranus and Neptune, cold as they are, emit a faint warmth from their interiors. A planet 5 to 10 times heavier than Earth, even if it sits hundreds of astronomical units from the Sun, would still radiate internal heat into space as infrared light. Infrared light is invisible to human eyes, but specialized telescopes can detect it. The challenge is building a telescope sensitive enough to catch the extremely faint thermal glow of a cold world sitting impossibly far away. Chen's team realized an existing telescope had already done the work. The Akari Space Telescope, a Japanese instrument launched in 2006, spent almost 2 years mapping the entire sky in infrared light before its coolant ran out and its most sensitive detectors stopped working. The data it collected sits in an archive, a complete thermal map of the entire sky that astronomers have only partially analyzed. Chen's team went into that archive looking for something that moved. Background stars and galaxies stay fixed. A planet in our solar system moves against that fixed background. Slowly, at first, almost imperceptibly, but over months, the shift becomes measurable. If Planet 9 appeared in the Akari data, it would show up as a faint infrared source that had moved between observations taken months apart. Chen's team searched the archive with this method. They focused on the region of the sky where Planet 9's orbit was predicted to place it, and they found 2 objects, 2 faint infrared sources, moving exactly as slowly as a distant planet should move, sitting exactly in the right region of the sky, emitting exactly the right amount of heat for a world of the predicted mass and distance. The astronomy community did not stay quiet for long. Telescopes have found remarkable things. Galaxies 13 billion light-years away, planets orbiting other stars by measuring tiny wobbles in starlight, black holes by watching stars orbit invisible points in space. But Planet 9 might be the hardest object to find in the entire history of astronomy. The problem is light, specifically, the lack of it. Every telescope on Earth and in orbit that uses visible light, the kind your eyes can see, works by collecting photons. Those photons either come directly from a light source, like a star, or they bounce off a surface and travel to the telescope, like sunlight reflecting off a planet. Mercury is close to the Sunday. It sits bathed in powerful sunlight. Even a backyard telescope can spot it on the right night. Planet 9 sits somewhere between 400 and 800 astronomical units away. At 400 astronomical units, the sun's light has spread out so enormously that its intensity drops to roughly 1 part in 160,000 of what it is at Earth's distance. At 800 astronomical units, that number drops further still. The tiny amount of sunlight that reaches Planet 9 then has to reflect off its surface, spread out in all directions, and travel hundreds of astronomical units back to Earth. The fraction of original sunlight that finally reaches our telescopes would be staggeringly small. Here is an analogy. Imagine you are standing in a stadium at midnight with every light off. Someone on the other side of the stadium is holding a piece of paper. A single flashlight pointed at the paper from an enormous distance away provides the only illumination. You have to spot the paper from across the dark stadium by the tiny amount of reflected light it produces. That is roughly the challenge of finding Planet 9 with visible light telescopes. Scientists tried. Years of sky surveys covered enormous patches of space, searching for a slow-moving faint dot against the fixed background of stars. Nothing confirmed. Multiple candidates turned up and were later ruled out. The planet, if it exists, continues to hide. The breakthrough came from changing the question. Instead of asking where Planet 9 reflects light, Amos Chen and his team asked where Planet 9 generates heat. Planets do not just reflect light. They also emit radiation from their own internal energy. For planets close to the Sun, this internal heat is minor compared to the sunlight they absorb and reflect. But for an object at Planet 9's predicted distance, where incoming sunlight is essentially zero, the internal heat becomes the dominant signal. It is faint, but it exists, and it radiates in infrared wavelengths that visible light telescopes cannot see, but infrared telescopes can. The AKRE telescope was built for exactly this kind of observation. It saw the sky in a wavelength range that no ground-based telescope can access cleanly, because Earth's atmosphere absorbs most infrared radiation before it reaches the ground. What Akari saw, and what Chen's team found buried in its archived data, changed the shape of the Planet 9 debate. The details of that discovery reveal something unexpected about how close the answer might actually be. In 2006, Japan launched a satellite into a sun-synchronous orbit around Earth. The AKRE telescope was built with one purpose: to see the universe in infrared light, the kind of light that carries heat. Earlier infrared missions had mapped parts of the sky. Akari's mission was more ambitious. Map all of it, every patch of sky, every direction. A complete thermal portrait of the entire observable universe from Earth's orbit. To do this, Akari carried a telescope cooled to near absolute zero using liquid helium. The extreme cold was necessary, for the same reason a dark room is necessary for photography. If the telescope itself was warm, its own heat would flood the detectors with infrared light, drowning out the faint signals from distant objects. By cooling the telescope to within a few degrees of the coldest possible temperature, engineers reduced the instrument's own interference to almost nothing. Akari began its all-sky survey and spent roughly 16 months scanning the entire sky systematically. The satellite completed multiple passes over the same regions of sky at different times, which turned out to be crucial for the Planet 9 search. Multiple passes mean multiple timestamps. Multiple timestamps mean you can check whether any object moved between observations. Background galaxies do not move. Background stars barely move. A planet in our solar system, even one sitting hundreds of astronomical units away, does move. Slowly but detectably, over months. When Akari's liquid helium coolant finally ran out in 2007, its most sensitive infrared detectors stopped working. The mission's primary survey was complete. The data went into an archive maintained by the Japan Aerospace Exploration Agency, available to researchers who wanted to dig through it. Most of the archive was used for other purposes: galaxy surveys, star formation studies, dust mapping in the Milky Way. The massive dataset sat largely unexplored for specific planet searches because the analysis required to identify a slowly moving object across multiple sky passes is complex and time-consuming. Amos Chen's team spent months developing a method to automate this search. They wrote software that combed through AKRE's sky maps, looking for infrared sources that appeared in multiple observations, but shifted position between passes. The region they focused on was the patch of sky where Planet 9's theoretical orbit places it based on the gravitational clustering of the outer solar system objects. Different research teams had published slightly different predictions for Planet 9's exact location, but there was general agreement about a broad region of the southern sky where the planet was most likely to be found. Chen's team pointed their software at that region. The search identified multiple candidates. Most were quickly ruled out. Galaxies can mimic the infrared signature of a cold, distant planet if the analysis is not careful. Detector artifacts in the data can create false signals. The team worked through each candidate systematically, eliminating everything that did not pass the tests. 2 objects passed every test. 2 infrared sources, moving at the right speed, positioned in the right region, radiating at the right thermal wavelength for a planet of the predicted mass and distance. The discovery announcement landed in June 2025, and the astronomy world split immediately into 2 camps: those who thought the candidates were real, and those who thought they might be something else entirely. Chen's team published their results in the Publications of the Astronomical Society of Australia. The paper described 2 sources of infrared light sitting in the predicted region of Planet 9's orbit. Both objects appeared in the Akari data. Both showed measurable movement between observations, taken months apart. Both emitted infrared radiation in the wavelength range and intensity expected from a planet between 5 and 10 Earth masses sitting at the distance Planet 9's orbit demands. Over a single 24-hour period, each object looked completely stationary, like a distant star, like background noise, like nothing interesting at all. Over several months, they moved, just barely, but detectably. That combination, frozen on a daily timescale but slowly drifting over months, is exactly the fingerprint of an extremely distant solar system object. A nearby asteroid moves visibly in a single night. A distant sednoid like ammonite shifts over weeks. An object at Planet 9's predicted distance would move even more slowly, requiring months of observation to confirm motion. The 2 Akari candidates behaved precisely as a planet at 800 astronomical units should behave. To understand how significant the location is, consider the prediction. Scientists built the Planet 9 hypothesis by analyzing the gravitational clustering of outer solar system objects. They ran statistical models. They calculated orbits. They published predictions about where in the sky Planet 9 should currently be sitting in its orbit. Multiple teams working independently produced overlapping predictions pointing to a specific broad region of the sky. Chen's 2 candidates sit in that region. This is the kind of result that produces cautious excitement in the scientific community. The candidates fit the prediction in multiple independent ways. The position matches. The thermal emission matches. The motion rate matches. Each of those agreements is unlikely by chance on its own. 3 agreements simultaneously narrows the probability of a coincidence dramatically. The candidates also fit no obvious alternative explanation. They do not appear to be known types of galaxies emitting similar radiation. They do not match any catalogued objects in the region. They moved, which rules out fixed background sources. But the team was careful in their announcement. The paper explicitly stated that follow-up observations are required to confirm whether these candidates are genuine solar system objects or some form of more distant background source, producing a convincing imitation of a planet's thermal signal. The announcement drew immediate attention from the broader astronomy community. Other researchers began planning follow-up observations. The question of what these 2 objects actually are has become one of the most urgent in planetary science. Confirming even one of them as a real planet would be the most significant discovery in solar system science since Neptune was found using a pencil and a prediction in 1846. But confirming them requires more than the Akari data alone, and in the meantime, the tension between the 2 competing narratives grew sharper. Ammonite says Planet 9 is gone or much farther away. The aka Ari candidates say it is right there in the predicted location. Both findings rest on real data from real instruments. The resolution of this contradiction will define the next chapter of planetary science, and what comes next is stranger than either team expected. 5 to 10 Earth masses. That number appears in every Planet 9 paper, every prediction, every thermal model. 5 to 10 times heavier than our entire planet. So what does that actually look like? Earth has a diameter of about 8,000 miles. 5 Earth masses would produce a planet somewhere between the size of Earth and Neptune. 10 Earth masses would be roughly Neptune's size. Neptune has a diameter of about 30,000 miles, nearly 4 times wider than Earth. A planet 9 at 10 Earth masses would be a world so large that Earth would look like a golf ball placed next to a basketball. A planet that size is not small. Jupiter, the largest planet in our solar system, is 11 times wider than Earth. Planet 9, at the high end of predictions, would be about a third of Jupiter's diameter. That is an enormous object, visible from space, reflecting sunlight, radiating heat. So how is it hiding? Distance. Pure, unforgiving distance. At 500 astronomical units from the Sun, a planet the size of Neptune produces a reflected light signal roughly 4 billion times fainter than Neptune itself. Neptune is already difficult to see with the naked eye. A planet Neptune's size, at 500 astronomical units, is completely invisible to any optical telescope currently operating on Earth or in orbit. But the heat is real. Every planet contains leftover energy from its formation. When dust and rock and gas collapsed to form a planet billions of years ago, the energy of that collapse compressed into heat. For planets close to the Sun, this internal warmth is small compared to the solar radiation they absorb and re-radiate. But cut off a world from all solar heating, push it hundreds of astronomical units into the dark, and the only warmth it has left is what formed inside it billions of years ago, slowly leaking out into space as faint infrared light. Planet 9 at 5 to 10 Earth masses, sitting at 500 to 800 astronomical units, would produce surface temperatures around -400 degrees Fahrenheit, frozen solid, dark, radiating an infrared signature roughly 100,000 times fainter than what Akari was designed to detect at its most sensitive settings. And yet, Chen's team found 2 candidates that fit. The margin is razor thin. The signals Chen's team identified sit at the edge of what Akari could detect. The telescope was not built for this specific search. The resolution of the data was not designed for objects this faint or this distant. Finding anything at all at this sensitivity level required months of careful analysis and a search algorithm built specifically for this problem. If the candidates are real planets, they represent a detection at the absolute boundary of what existing technology can achieve. If they are something else, background galaxies or detector artifacts that survive the team's filtering process, it means Planet 9 remains completely undetected by every instrument ever built. That uncertainty is not a failure of science. It is the edge of the known, and right at that edge, 2 faint heat signals are sitting in the dark, waiting for a telescope powerful enough to tell us what they actually are. The answer may come sooner than most people realize. Picture a clock with hands so slow you cannot see them move. You stare at it for a minute. Nothing. You look away. Come back an hour later. The hands have shifted, but you never caught them moving. The motion only becomes real when you compare 2 moments far enough apart. That is exactly how the Akari candidates behave. And understanding why reveals something remarkable about the physics of orbital speed at extreme distances. Everything in the solar system orbits the Sunday, but orbital speed drops with distance. Mercury, the closest planet, races around the Sun at about 30 miles per second. Earth travels at about 19 miles per second. Neptune, sitting 30 times farther from the Sun than Earth, moves at only about 3.5 miles per second. The rule is simple. The farther you sit from the Sun, the slower you move. Planet 9, sitting somewhere between 500 and 800 astronomical units away, moves at a speed so slow it barely registers against the background of the sky. Scientists calculate that a planet at that distance would take somewhere between 10,000 and 20,000 years to complete one full orbit. In a single human lifetime, it would cover a tiny fraction of its total path. Translated to what a telescope sees, this means the planet shifts its position in the sky by a tiny amount each year. Over 24 hours, the shift is so small it falls below the detection threshold of most instruments. The planet looks exactly like a stationary background object. Over months, the shift accumulates. Not dramatically, not obviously, but enough that careful analysis of images taken at different times reveals a slow crawl against the fixed stars behind it. This is precisely what Chen's team found in the Akari data. Each candidate appeared in multiple sky passes separated by months. In each individual pass, the object looked stationary. Between passes, it had moved. The movement rate matched the predicted drift speed of an object at Planet 9's expected distance. The match is not approximate. The rate of drift, the direction of movement, and the position in the sky all align with predictions made years before Chen's team even began their search. This kind of predictive match is what elevates a candidate from interesting to compelling. Anyone can find a faint object in a sky survey, but finding a faint object that moves at exactly the right speed, in exactly the right direction, from exactly the right location, while also emitting exactly the right amount of infrared heat, stacks coincidences in a way that becomes scientifically difficult to dismiss. The team remained cautious in their language. Cautious is the right word here. Astronomy has produced false positives before. The history of Planet 9 searches includes multiple candidates that dissolved under closer inspection. Every scientist involved in this field has learned to check, recheck, and check again before announcing anything final. But the caution does not change the data. The candidates are real signals in a real telescope's archive. They behave the way a real planet should behave. And until a more powerful telescope either confirms or rules them out, they represent the strongest observational case for Planet 9's existence ever published. What that confirmation would mean reaches far beyond astronomy. Astronomers have been hunting for a planet beyond Neptune for longer than most people alive today have been alive. The idea did not start with Planet 9. It started with Planet X, a name given to any hypothetical world beyond the known planets. The search is old. After Neptune was discovered in 1846, by predicting it from Uranus's wobbly orbit, astronomers immediately wondered whether another undiscovered planet was pulling on Neptune the same way. The hunt for Planet X began almost immediately. Pluto was found in 1930 by a young astronomer named Clyde Tombaugh, scanning photographic plates one by one at the Lowell Observatory in Arizona. For decades, scientists hoped Pluto was Planet X, but Pluto turned out to be far too small to explain Neptune's orbital variations. The hunt continued. Decades passed. Better telescopes came online. Sky surveys improved. And slowly, the outer solar system began revealing its population. Thousands of small, icy objects beyond Neptune. The Kuiper Belt, then Sedna, in 2003, sitting in its impossibly remote orbit and demanding an explanation. In January 2016, two astronomers at the California Institute of Technology, Konstantin Batygin and Mike Brown, published a landmark paper. They had analyzed the orbits of 6 distant Kuiper Belt objects and found that they clustered in a way that random chance could not explain. Their mathematical analysis pointed to a single conclusion. A planet between 5 and 10 Earth masses was orbiting the outer solar system and gravitationally herding these objects into alignment. They named it Planet 9. The paper immediately split the astronomy community. Some researchers found the statistical argument compelling. Others pointed out that 6 objects was a small sample, and the clustering might be a selection bias caused by the difficulty of finding objects in certain parts of the sky. The debate has never fully resolved. In the 9 years since that 2016 paper, multiple sky surveys have searched for Planet 9, the Subaru telescope, the Dark Energy Survey, dedicated infrared searches. None produced a confirmed detection, until Chen's team searched the Akari archive in 2025. If the 2 thermal candidates are confirmed as real, the gap closes. 40 years of searching, from the early Planet X hunts to modern infrared astronomy, culminating in the identification of 2 heat signatures sitting in the dark at the edge of the solar system. But here is the discomfort that lives inside this timeline. During those 40 years, ammonite was also discovered, and ammonite does not cooperate. The same year, Chen's team published their thermal candidates. Huang's team published the ammonite paper, showing that the standard Planet 9 hypothesis is undermined by the new Sednoid's orbit. Two landmark papers, two opposite conclusions, published within weeks of each other in 2025. The 40-year hunt has not ended. It has reached its most complicated and fascinating moment yet. Science is supposed to converge. You run experiments, collect data, compare results, and gradually the truth comes into focus. Different teams studying the same problem should move toward agreement over time. That is how science is supposed to work. Planet 9 is doing the opposite. In the summer of 2025, two separate research teams published results that flatly contradict each other. Both used rigorous methods. Both published in respected peer-reviewed journals. Both have legitimate scientific standing. Huang's team, working in Japan, analyzed Ammonite's orbit using orbital mechanics and computer simulation. Their conclusion: the standard Planet 9 hypothesis is significantly less likely than previously believed. Ammonite's survival requires either that Planet 9 is much farther away than predicted, or that no planet currently exists at the predicted location at all. The ejection scenario, a past giant planet now gone, fits the data better. Chen's team, working in Taiwan, analyzed infrared data from the Akari satellite archive. Their conclusion: two objects sit in the exact predicted location of Planet 9, moving at the exact predicted speed, emitting the exact predicted amount of heat. Planet 9 is there, right now, waiting to be confirmed. Both teams are right about their own data. The conflict is not about bad science. It is about what the data means and which interpretation survives when the full picture comes together. Several explanations could resolve the contradiction. 1. Planet 9 exists but sits farther away than the standard models predict. This would explain why Ammonite's orbit survived, because a more distant planet exerted less gravitational force on it. And the Akari candidates could represent this more distant version of the planet, sitting at the outer edge of the predicted range. 2. Planet 9 does not exist, and the Akari candidates are background galaxies or other distant objects that mimicked a planet's thermal signal closely enough to survive Chen's filtering process. Ammonite's orbit would then be explained by ancient forces, a passing star or early star cluster, with no current hidden planet required. 3. Planet 9 exists, but there are actually two of them, two separate hidden planets, each shaping different populations of outer solar system objects differently. This would explain why Ammonite points a different direction from the other three Sednoids, and why the Akari search found two candidates instead of one. That third option sounds extreme, but astronomers have seriously proposed it. Systems with multiple giant planets in wide orbits exist around other stars. There is no physical rule that prevents our outer solar system from harboring more than one hidden world. The resolution of this conflict depends entirely on follow-up observations, and the instruments needed to perform those observations are either already in operation or coming online within years. What astronomers find next will settle one of the longest-running debates in the history of planetary science. The pressure is building, and the history of the debate itself explains why this moment feels different from every previous false alarm. Every planet hunter's nightmare has a name: false positive. The history of astronomy is full of candidates that turned out to be something else. Signals mistaken for planets, artifacts in data that mimicked real objects, detections that evaporated under scrutiny. The Akari candidates face exactly this risk. Here is the specific problem. Galaxies are everywhere in the sky, hundreds of billions of them, scattered in every direction, at every distance. Most are so far away and so faint that they blur into background noise. But some emit infrared light in wavelengths and intensities that overlap with what a cold, distant planet would produce. These are called infrared luminous galaxies. Some are galaxies undergoing rapid star formation, which generates enormous heat. Some host active supermassive black holes at their centers, which heat the surrounding dust and gas to temperatures that radiate strongly in infrared wavelengths. At extreme distances, these objects can appear small, faint, and point-like, exactly like a distant planet would look. Chen's team built filters to catch these imposters. They used the motion test as the primary discriminator. Galaxies, even distant ones, do not move against the background of other galaxies on the timescale of months. A solar system object moves. If something in the AKRE data appeared to move between sky passes, it was a strong candidate for a real planet. But here is the trap. AKRE's resolution was limited. The telescope was an impressive scientific instrument, but it was designed for an all-sky survey, which means breadth over precision. Individual point sources in the data have position uncertainties measured in arcseconds, tiny fractions of a degree, but large enough that the apparent movement between sky passes might not be real motion. It could be measurement uncertainty. If the apparent movement of the two candidates falls within the positional uncertainty of the AKRI data, then the candidates might actually be stationary background sources. Galaxies sitting billions of light-years away, radiating infrared heat at wavelengths similar to a cold planet, and appearing to move only because the telescope could not pin down their positions precisely enough. This is what keeps astronomers awake. The candidates are real signals. Nobody disputes that. Two faint infrared sources sitting in the predicted region. Real, confirmed in the archive. But whether they are moving solar system objects or stationary background galaxies cannot be determined from AKRE data alone. The resolution is simply not sufficient. The only way to answer the question is with a more precise telescope, one that can image the candidates with enough resolution to either detect genuine movement or confirm they are stationary. Several observatories around the world have the capability to attempt this follow-up. The James Webb Space Telescope has extraordinary infrared sensitivity. Ground-based infrared observatories in Chile and Hawaii have the resolution to distinguish real motion from measurement noise. The observations are being planned. The race is on, and the outcome will do more than solve the Planet 9 mystery. It will determine whether Ammonite's impossible orbit is a clue pointing to a missing planet or a clue pointing to something that was here long ago and left without looking back. 8 planets is the answer on every school test, every poster on every classroom wall. 8 planets, in order, memorized and repeated. But planetary scientists have spent decades quietly questioning that number. The solar system formed from a disk of gas and dust. That disk contained enough material to build far more than 8 planets. Computer models of planet formation regularly produce 10, 12, or even 15 planets in early solar system simulations, before gravitational interactions reduce the number through collisions and ejections. The question scientists argue about is not whether additional planets could have formed. The physics says they almost certainly did. The question is how many survived. The Nice model, developed by a group of researchers in Nice, France, and published in 2005, was a landmark attempt to explain the current structure of the solar system. The model proposed that the early solar system's giant planets started in different positions and migrated to their current orbits over hundreds of millions of years. The gravitational chaos caused by this migration could explain the late heavy bombardment, the structure of the Kuiper belt, and several other features of the solar system that simpler models could not account for. Early versions of the Nice model worked best with 5 giant planets, 4 that survived to become Jupiter, Saturn, Uranus, and Neptune, and 1 that was ejected during the chaotic migration period. This is confirmed as a scientifically serious scenario. The Nice model is not fringe thinking. It has been refined repeatedly over 20 years and remains one of the most successful frameworks for understanding the solar system's history. And it requires a planet to have been thrown out. If the ejected planet hypothesis is correct, then the solar system once had 9 planets in total, and the 9th was expelled in the ancient past. Before humans, before life on land, before complex, multicellular organisms existed on Earth, Planet 9, in this scenario, is a ghost, the mathematical trace of something that used to be here. But the other possibility is that the ejected planet in the Nice model was a smaller world, and a separate massive planet is still orbiting today, having survived the chaos of the early solar system in a stable, distant orbit. These two possibilities are not mutually exclusive. The solar system could have ejected one planet early and still harbor a different large planet in a stable, distant orbit right now. The number 8 on those classroom posters may need a question mark attached to it. What comes next in this story reaches back to 1846, to the last time a planet was added to our solar system, and traces the unbroken line of discovery that leads directly to the controversy of today. On September 23rd, 1846, a German astronomer named Johann Galle pointed his telescope at a precise spot in the sky, based on a set of calculations sent to him by a French mathematician named Urbain Le Verrier. He found Neptune within 1 degree of the predicted location. On the first night, the method Le Verrier used was orbital mechanics. Uranus, the 7th planet, was not moving exactly as Newton's laws of gravity predicted. Something was pulling on it. Le Verrier worked backward from the discrepancy, calculated the mass and location of the object causing the pull, and sent his prediction to Berlin. It was the first time a planet was found by mathematics before it was found by a telescope. That success launched a template. If planetary gravity leaves fingerprints in the orbits of other objects, and if those fingerprints can be calculated precisely enough, mathematics can find planets before eyes do. Astronomers immediately began looking for similar discrepancies in Neptune's orbit. Some believed they found them. The Planet X hunt began within years of Neptune's discovery. Clyde Tombaugh found Pluto in 1930, but Pluto was far too small to account for the orbital discrepancies that motivated the search. Later analysis showed those Neptune discrepancies were actually measurement errors in the early data. The irregularities vanished when more precise measurements were collected. Pluto's discovery turned out to be a coincidence of coordinates rather than a triumph of prediction. But the lesson stayed. Mathematics can point to hidden objects in the solar system. The method works. Neptune proved it beyond any doubt. When Sedna appeared in 2003 with its impossible orbit, astronomers remembered Neptune. They remembered Le Verrier. They remembered that gravitational fingerprints in orbital data can reveal something invisible. In 2016, Batygin and Brown essentially repeated Le Verrier's logic, but applied it to the clustering of outer solar system objects instead of Neptune's orbital wobble. They found a gravitational fingerprint in the orbital patterns of 6 distant objects. They calculated backward to find the mass and location of the object producing that fingerprint, and they published a prediction. The prediction points to a region of the sky. Chen's 2 thermal candidates sit in that region. If the candidates are confirmed, the chain of logic runs unbroken from Le Verrier's pencil calculations in Paris in 1845 to an infrared satellite archive in 2025. Almost 180 years of the same idea, tested again and again, finally producing a result. That chain is what makes the current moment feel different from every previous Planet 9 claim. The prediction came first. The data appeared after. That is the order science requires. Konstantin Batygin was 30 years old when he and Mike Brown published their Planet 9 paper in January 2016. Brown was already famous in astronomy circles. He had discovered Sedna and dozens of other Kuiper Belt objects. He was the astronomer most responsible for Pluto's reclassification as a dwarf planet in 2006. His nickname in the press became the man who killed Pluto. When Brown and Batygin published together, the astronomy world paid attention. Their argument rested on 6 distant Kuiper Belt objects, with orbits that clustered in a statistically unusual way. The orbits all stretched toward the same region of space. The angles of their orbital planes aligned more than random distribution should allow. Batygin and Brown calculated the odds of this clustering occurring by chance at roughly 1 in 15,000. Those odds are low enough to take seriously. Their mathematical model showed that a single planet between 5 and 10 Earth masses, orbiting the Sun at a distance of 400 to 800 astronomical units, could produce the observed clustering through gravitational influence over billions of years. The planet would be in a highly elongated orbit, tilted about 30 degrees relative to the plane most planets orbit in. The paper immediately split the community. Supporters pointed to the statistical argument and the elegance of a single planet explanation that unified multiple otherwise puzzling features of the outer solar system. Critics raised the sample size problem. 6 objects was not many. The surveys that found those 6 objects covered the sky unevenly, making some regions easier to search than others. If the regions where clustered objects were found happened to be the most thoroughly surveyed regions, the clustering might be an artifact of where astronomers looked rather than a real gravitational signal. This is called observational bias. It is one of the most common pitfalls in astronomy. You find more objects where you look more carefully. If you looked more carefully at one part of the sky, the objects you found there will naturally cluster in that part of the sky, even if the actual distribution of objects is random. Subsequent surveys attempted to correct for this bias by searching areas of sky that had been less thoroughly covered. Some found additional clustered objects that seemed to support Planet 9. Others found objects that did not cluster, weakening the statistical case. The debate has never definitively resolved. Ammonite added fuel to the skeptical side. The Akari candidates added fuel to the supporting side. And the astronomy community remains divided, not out of stubbornness, but because the evidence genuinely points in both directions, depending on which dataset you weight more heavily. The resolution requires a direct detection, and the instruments that could achieve that detection are now operational, or nearly so. Ammonite has been traveling the same path since before Earth had continents. 4.5 billion years of orbiting. The same loop, the same perihelion 66 astronomical units from the Sunday. The same slow arc through the outer solar system, taking thousands of years per complete revolution. Unchanged since the solar system was barely formed. That stability is the key fact scientists keep returning to, because stability at that distance, in that specific gravitational dead zone, is not automatic. It requires the right conditions at the right time. Think of it like a coin balanced on its edge. Coins do not randomly balance on their edges. Something placed it there, precisely, at a specific moment. The coin has no mechanism to correct itself if it wobbles. It survives only because whatever force balanced it was precise enough and the conditions afterward were calm enough to let it stay. Ammonite is that coin. Whatever force placed Ammonite in its current orbit had to be powerful enough to push it from its original formation zone, far from the Sun, and precise enough to put it in an orbit that would remain stable for billions of years. Too much force, and Ammonite gets thrown into interstellar space. Too little force, and Ammonite stays in the inner Kuiper belt where Neptune's gravity can reach it and gradually disrupt its path. The precision required points to either a very specific gravitational event or a prolonged interaction with something massive. Computer simulations confirm this. The team that discovered Ammonite ran thousands of simulated solar systems, varying the conditions of the early solar system and testing which scenarios could produce Ammonite's current stable orbit. Most scenarios fail. Most either send a virtual Ammonite into interstellar space or leave it in an unstable orbit that eventually collapses back toward the inner solar system. The scenarios that succeed tend to involve either a close passage by a star billions of years ago or a massive planet that gravitationally nudged Ammonite into its current path before either stabilizing in a distant orbit or being ejected. Both of these scenarios have happened in other solar systems. Scientists have observed other star systems with evidence of past stellar flybys. The early Sun almost certainly spent time in a stellar nursery, a dense cluster of young stars where close approaches between star systems were common. But here is what makes Ammonite special beyond all the theoretical arguments. Ammonite is real, measured, confirmed. Its orbit is not a model output or a prediction. It is an observation. Every theory about the outer solar system now has to explain Ammonite, and most of them struggle. The ones that do not struggle are the ones that involve a past catastrophe, a violence so complete that the outer solar system was rearranged and then froze in place with ammonite as one of the surviving witnesses. Understanding what that catastrophe might have looked like requires something beyond the current data. It requires a new generation of telescopes powerful enough to see what no instrument has managed to see yet. Every telescope ever built has a limit. The limit might be the size of its mirror, or the wavelength of light it can detect, or the sensitivity of its detectors, or the resolution of its images. Every instrument hits a wall, and beyond that wall, the universe stays hidden. Planet 9 sits behind the wall of every telescope currently in operation. If Planet 9 exists and sits at 500 astronomical units, its reflected light is roughly 10 billion times fainter than the faintest object visible to the naked eye. Current ground-based optical telescopes cannot detect reflected sunlight from an object that distant. The AKARI infrared data shows heat signatures that could be the planet, but AKARI's resolution is too low to confirm them as moving solar system objects. What scientists need is a telescope that combines three capabilities simultaneously: high infrared sensitivity to detect faint thermal glow, high spatial resolution to confirm motion over months, and wide enough sky coverage to systematically sweep the predicted region rather than targeting one small patch at a time. Two telescopes stand out as the most capable candidates for this confirmation. The first is the James Webb Space Telescope. Already operating in space since 2022, Webb sees the universe in infrared light with extraordinary sensitivity and resolution. If the two AKA candidates are genuine planets, Webb could image them precisely enough to confirm their motion and rule out background galaxy contamination. The limitation is sky coverage. Webb observes specific targets rather than scanning broad regions systematically. Astronomers would need to know approximately where to point it. The AKARI candidates give them a starting position. The second is the Vera Rubin Observatory in Chile, which began science operations in 2025. Rubin is built for exactly the kind of wide-field systematic sky survey that Planet 9 searches require. Its primary mirror is over 27 feet wide, and its camera is the largest digital camera ever built for astronomy. It will systematically image the entire southern sky every few nights for 10 years, building a catalogue of every moving object it can detect. Planet 9, if it exists, will move against the background of fixed stars during Rubin's decade-long survey. The movement will be slow, tiny, but Rubin's repeated imaging of the same sky patches will accumulate enough data to detect even that glacial drift. The combination of these two telescopes, Webb for precise targeted follow-up and Rubin for wide-field systematic hunting, represents the best chance humanity has ever had to settle the Planet 9 question. Scientists estimate that if Planet 9 exists in the predicted region and within the predicted mass range, the Rubin Observatory should detect it within its first 5 years of operation. That is not a guarantee. Planet 9 has hidden this long. It may still find ways to remain hidden, but the odds of it surviving another decade of these instruments are slim. The answer is coming, and the answer will reshape how we understand our place in this solar system. If Planet 9 is confirmed, consider what that means. For all of recorded human history, our solar system has contained an unknown giant planet. Every civilization that ever looked at the night sky was sharing this solar system with something they could not see. The ancient Babylonians mapped the sky with extraordinary precision. The Greeks calculated Earth's circumference. Medieval astronomers charted the stars, night after night, for centuries. Planet 9 sat there the entire time, enormous, invisible. Every scientific instrument built since Galileo pointed his telescope at the moon in 1609 has failed to find it. The discovery of Uranus in 1781, Neptune in 1846, Pluto in 1930, thousands of asteroids and comets and Kuiper Belt objects all happened while Planet 9 waited undetected. That invisibility is not a failure of science. It is a consequence of distance. At 500 to 800 astronomical units from the Sun, no instrument built before the infrared space age had any possibility of detecting it. The physics simply did not allow it. But the scale is still staggering. A world 5 to 10 times heavier than Earth, somewhere between the size of a basketball and a larger ball compared to Earth as a golf ball, has been orbiting our sun for 4.5 billion years without anyone knowing, and its effects have been real the whole time. If Planet 9 exists and has been exerting gravitational influence on the outer solar system for billions of years, it has been shaping the paths of comets and small bodies in ways we never accounted for. Long-period comets that fall into the inner solar system on thousand-year trips from the outer reaches may have been nudged toward their current trajectories by Planet 9's gravity. Some of those comets hit planets. Some may have hit Earth. The connection between a hidden, distant planet and impacts on Earth is not direct. The chain of gravitational influence is long and diffuse. Scientists are careful to avoid overstating the link. But the outer solar system is not a static place. Objects get nudged, trajectories change. Things that were once stable become unstable over millions of years. A planet 10 times heavier than Earth, orbiting at hundreds of astronomical units for 4.5 billion years, has touched the outer solar system in ways that radiate through the entire system over time. The confirmation of Planet 9 would require a complete revision of the outer solar system models. Every simulation, every prediction about comet pathways, every model of how the solar system evolved would need updating to account for a force that was always there but never included. That scientific revision would take years. The discoveries waiting inside it are impossible to predict, but they start with confirming whether those two faint heat signatures in the Akari archive are real. Long-period comets are the solar system's slowest missiles. They form in the distant Oort cloud, the vast shell of frozen material surrounding the solar system at distances up to 100,000 astronomical units from the Sunday. Gravitational nudges from passing stars, or the gentle pressure of the galaxy's gravity, occasionally push one of these frozen objects off its stable path and send it falling inward toward the Sunday. The journey takes thousands of years. The comet accelerates as it falls, reaching tens of miles per second by the time it passes through the inner solar system. It swings around the sun, blazes visibly for weeks or months as its ice boils off in the solar heat, then recedes back into the deep outer solar system. Some long-period comets return on cycles of thousands of years. Some are thrown out of the solar system entirely by a close encounter with a planet. Some, historically, have hit planets. Planet 9's gravity sits in a region, the outer solar system, where comets pass on their long inward journeys. A planet 5 to 10 times heavier than Earth generates a gravitational field that extends significantly into the surrounding space. Objects passing within a certain range of Planet 9 during their fall toward the inner solar system would receive gravitational kicks, their trajectories bent slightly by the planet's pull. In most cases, these kicks are minor. The comet continues inward, follows a slightly altered path, and either completes its journey or misses the inner solar system entirely. In some cases, the kick is stronger. Planet 9's gravity could redirect a comet that would otherwise have remained in the outer solar system, sending it on a trajectory that brings it much closer to Earth's neighborhood than it would have reached on its own. Scientists studying this effect have found it is a real but statistically minor influence. Planet 9, if it exists, has probably redirected some comets toward the inner solar system over billions of years. The increase in comet flux that it would cause, compared to a solar system without it, is estimated to be small enough that it does not dramatically change the probability of a major Earth impact on any human timescale. This is a theory with confirmed physical logic but unquantified historical impact. The number of comets Planet 9 has redirected in 4.5 billion years is genuinely unknown. What scientists can say is this: the inner solar system has been hit by long-period comets throughout Earth's history. Some of those impacts were enormous. Some may have triggered mass extinction events. The gravitational architecture of the outer solar system played a role in determining which comets fell inward and which ones stayed out. If that architecture includes Planet 9, then Planet 9 has been a background factor in Earth's history all along. That connection does not justify alarm. The risk is real but diffuse, stretched across billions of years and dwarfed by closer threats. But the idea that an unknown giant planet has been quietly shaping Earth's story from 500 astronomical units away is the kind of truth that changes how you think about the solar system we live in. 4. Sednoids. That is the complete known population of objects in the extreme outer solar system. 4 worlds discovered in over a century of sky surveys. In a solar system 4.5 billion miles across at its inner edges and extending to almost a full light year at the outer boundary of the Oort cloud, 4 detected objects in a specific orbital zone tells you almost nothing about the true population. Scientists estimate that for every sednoid we have found, hundreds or thousands more exist. The math is straightforward. Sednoids are small, dark, frozen, and enormously far away. They reflect almost no light. They emit almost no detectable heat with current instruments. The surveys that found all 4 existing sednoids covered a tiny fraction of the sky, with the sensitivity needed to spot objects that faint. The regions of sky not surveyed, or surveyed only with older, less sensitive instruments, could contain many more sednoids in orbits scientists have never glimpsed. If the true population of sednoids numbers in the hundreds, the clustering argument for Planet 9 becomes far more complicated. 3 out of 4 sednoids clustering sounds statistically significant. 3 out of 400 sednoids clustering in one direction, with the other 397 scattered randomly in all directions, sounds like a coincidence. The current evidence cannot distinguish between these 2 pictures, but the situation extends beyond sednoids. The Kuiper Belt itself, the broad zone of frozen objects extending from Neptune's orbit outward to roughly 50 astronomical units, has been thoroughly surveyed only in patches. Large-scale surveys have found thousands of Kuiper Belt objects, but models of how the early solar system distributed material predict the belt should contain hundreds of thousands more objects that current surveys have not reached. Beyond the Kuiper Belt, in the region between roughly 50 and 300 astronomical units, survey coverage drops dramatically. Objects in this middle zone, sometimes called the scattered disk, are known primarily through serendipitous discoveries rather than systematic coverage. And beyond that, in the sednoid zone and the inner Oort cloud, the known population is essentially 4 objects. The Vera Rubin Observatory will change this dramatically. Its decade-long sky survey will push the detection limit for outer solar system objects to depths never reached before. Scientists expect Rubin to discover thousands of new Kuiper Belt objects, hundreds of scattered disk objects, and potentially dozens of new sednoids. Those new sednoids will be transformative. If the new sednoids discovered by Rubin cluster in the same direction as Sedna and the 2 others, the Planet 9 hypothesis gains enormous statistical power. If they scatter randomly in all directions, including the direction Ammonite points, the hypothesis weakens severely. The outer solar system contains the answer. Instruments are finally sensitive enough to read it, and the population of hidden worlds waiting to be found out there almost certainly includes objects no existing theory has predicted. On a mountain in the Chilean Atacama Desert, sitting at an altitude of almost 9,000 feet, a telescope is doing something no telescope has done before. The Vera Rubin Observatory completed its main mirror in 2021 and moved into science operations in 2025. Its primary mirror spans over 27 feet. Its camera contains more than 3 billion pixels, the largest digital camera ever built for astronomical use. Every few nights, it images the entire visible sky from its location in the southern hemisphere. The strategy is called the Legacy Survey of Space and Time. Over 10 years, Rubin will build the deepest and most complete map of the moving sky ever assembled. Every object that moves against the background of fixed stars will be detected, catalogued, and tracked as new images accumulate. For Planet 9 hunters, Rubin represents the first instrument capable of systematically covering the entire predicted region of the planet's orbit at the sensitivity required to actually see it. If Planet 9 exists at the high end of the predicted distance range, around 800 astronomical units, it sits right at the edge of Rubin's detection capability. The telescope should be able to spot it, but confirmation will require multiple observations spread across years to detect its slow movement with confidence. If Planet 9 sits closer, at the lower end around 400 to 500 astronomical units, Rubin should find it faster and with higher confidence. Scientists who support the Planet 9 hypothesis have estimated that if the planet is real and sits anywhere within the predicted range, Rubin should detect it within the first 5 years of full operations. That timeline places potential confirmation between 2025 and 2030. Beyond Planet 9 specifically, Rubin will transform the entire outer solar system database. Astronomers expect to discover tens of thousands of new Kuiper Belt objects, potentially hundreds of new scattered disk objects, and a dramatically larger population of sednoids. Each new sednoid either strengthens or weakens the clustering argument. Each new extreme outer solar system object gives scientists a new data point for testing whether a hidden planet's gravity is organizing the distant architecture of the solar system. The clustering question, which has driven the Planet 9 debate since 2016, will finally have a sample size large enough to answer conclusively. A dozen sednoids cannot settle the statistical debate. 100 sednoids can. Rubin's discoveries, combined with targeted follow-up observations from the James Webb Space Telescope and ground-based infrared observatories, create a scientific environment where the Planet 9 question is answerable within the current decade. Either Planet 9 will be found, confirming one of the most dramatic predictions in modern planetary science, or the outer solar system will reveal itself as a planet-free zone of scattered objects, and scientists will face the deeper question of what ancient force, a passing star, a dense stellar nursery, or some mechanism not yet imagined, put the sednoids in their impossible orbits. Both outcomes reshape our understanding of the solar system, and the stranger possibility waiting inside the data is the one nobody expected. Absence can tell you as much as presence. If the Rubin Observatory completes its survey and finds no Planet 9, that result carries enormous scientific weight. The predicted region gets covered. No giant planet appears. The hypothesis, at least in its standard form, dies. But that death opens a door. If Planet 9 is absent from where it should be, and if the sednoids still cluster, and if Ammonite still sits in its impossible gravitational dead zone, then something had to put them all there. The universe does not create anomalies without causes. The outer solar system contains a genuine mystery that demands a genuine answer. The ejection hypothesis steps forward in this scenario. A giant planet that existed 4.5 billion years ago shaped the outer solar system during its lifetime and was then thrown into interstellar space during the chaos of planetary migration, would leave exactly the pattern scientists observe today. Clustered sednoids, whose paths were herded by the planet's gravity during its existence. An object like Ammonite, whose orbit was shaped before the planet's departure and has been frozen ever since. A Kuiper belt with an inner edge and a structure that reflects the gravitational influence of a world that is no longer present to influence it. The scars of an ejected planet persist for billions of years. Orbits shaped by a giant planet's gravity do not immediately dissolve when the planet leaves. They persist, they freeze, they become the fossil record of a solar system that used to be different. This would require a fundamental shift in how planetary scientists communicate about our solar system. The standard model of 8 planets would be replaced by a historical model, acknowledging that our neighborhood once contained more, and that the architecture we observe today reflects a past trauma rather than a current equilibrium. For the field of comparative planetology, the study of how planetary systems form and evolve around other stars, the ejection scenario would be enormously valuable. Scientists already know that giant planet ejections happen in other systems. Finding strong evidence that one happened in our own would confirm that our solar system is not an unusually stable or well-ordered system, but a typical one that went through the same kind of violent reorganization most planetary systems experience. This matters because the stability of Earth's position in the solar system depends on the overall gravitational architecture. If that architecture was violently disrupted 4.5 billion years ago and then restabilized, Earth survived by accident as much as by design. The ejection scenario, confirmed, would tell us that the solar system we live in today is a survivor's version of a more chaotic original. And every feature of the current system, every orbit, every distance, every pattern we observe, carries the memory of that original violence. That is a different story than the clean 8-planet model taught in schools, but it is a truer one. 2 candidates. Chen's team found 2 infrared signals in the Akari data. The immediate assumption in most discussions is that one of them is Planet 9, and the other is a background contaminant, a false positive that will be ruled out when better observations arrive. But a few planetary scientists have proposed a different reading. What if both candidates are real planets? Multiple giant planets in wide outer orbits are not forbidden by physics. They exist around other stars. Systems with 2 or more giant planets in distant orbits have been detected through direct imaging around nearby young stars. The early solar system, with its chaotic migration period and abundant raw material, could plausibly have formed more than one large planet in the outer reaches. If 2 massive planets orbit the Sun at different distances and in different orbital orientations, they would each exert gravitational influence on different populations of outer solar system objects. One planet might be responsible for clustering the 3 sednoids that align together. The other might be responsible for Ammonite's very different orbital orientation. The contradictory evidence, Ammonite pointing the wrong way while the others cluster, has been the central puzzle since Ammonite was discovered. A 2-planet explanation resolves it neatly. 2 gravitational shepherds, each herding a different subset of outer solar system, objects into its own alignment. Ammonite falls under the influence of one shepherd. The other 3 sednoids fall under the other. This is a theory built on top of another theory, and scientists are appropriately cautious about stacking hypotheticals. But the scenario is physically plausible, and the discovery of 2 separate Akari candidates gave it unexpected observational support. If Rubin or Webb confirms both candidates as real planets, the solar system gets redrawn immediately. The discovery of one hidden giant planet would be historic. The discovery of 2 simultaneously would be the most significant event in planetary science since the invention of the telescope. The mass estimates for the 2 candidates, based on their thermal signals, both fall within the range of 5 to 10 Earth masses. 2 planets of similar mass in very different orbits would present a unique dynamical puzzle. How did they both end up in stable orbits? Did they form there? Did they migrate? Did they interact with each other during the early solar system and reach some kind of gravitational settlement? These questions have no answers yet. The candidates are unconfirmed. The 2-planet hypothesis is a serious suggestion from serious scientists, but it remains exactly that, a suggestion. What it reveals is how open the outer solar system still is as a scientific frontier. After centuries of planetary discovery, after all the probes and telescopes and mathematical models, the possibility remains that we have been sharing our solar system with 2 hidden giants, and we are only now, in 2025, getting the faintest thermal whisper of their existence. The final question this raises is the biggest one yet, and its answer stretches beyond our solar system entirely. Astronomy started as a story about our sky. Ancient observers tracked planets across the background of fixed stars, named them, built calendars around them, wrote myths. For most of human history, the solar system was the universe. Everything else was decoration. Then the scale expanded. Stars became suns, distant lights became galaxies, The observable universe, open to a sphere 13 billion light-years wide, containing hundreds of billions of galaxies, each with hundreds of billions of stars. And now, the scale has contracted back to our own backyard. Because the discoveries unfolding right now, Ammonite's impossible orbit, the two thermal candidates, the competing simulations, are generating questions that apply to every solar system in the galaxy. Here is the shift. Before the Planet 9 search, astronomers studying other planetary systems around distant stars saw the giant planets in wide orbits, with no clear framework for how they got there. Some systems have giant planets sitting at enormous distances from their stars. Some show evidence of past planetary ejections. Some have multiple giant planets in chaotic orbits. These observations were puzzling because the standard model of planetary formation did not predict them easily. The Planet 9 hypothesis and the evidence surrounding it offers a framework. Giant planets migrate during a solar system's early history. Their migrations cause collisions, ejections, and gravitational reorganizations that scatter smaller objects into extreme orbits. The systems we observe around other stars, with their distant giants and scattered debris, may all be survivors of the same kind of chaotic early period our own solar system went through. Sednoids like Ammonite might be universal. Every solar system that formed with multiple giant planets and went through a migration phase might have its own population of extreme objects sitting in frozen, distant orbits, preserving the memory of the chaos that shaped the system. If astronomers find Planet 9, they confirm that giant planet survival in wide, distant orbits is possible after a chaotic early history. This changes the statistical prediction for how many other solar systems have similar hidden worlds. If astronomers confirm the ejection scenario instead, they confirm that giant planet losses are common, and that the scattered debris those planets leave behind follows predictable patterns. This gives scientists a new tool for reading the history of planetary systems around other stars from the orbital signatures of their smallest objects. Either way, the outer solar system of our own small corner of the galaxy becomes a Rosetta Stone. Ammonite, sitting cold and silent 66 astronomical units from the Sun, is more than a frozen rock in a distant orbit. It is a message written 4.5 billion years ago. Scientists are learning to read it right now. The two heat signatures in the Akari archive are either the first glimpse of a world that has been here all along, or the ghost light of something else entirely. The Vera Rubin Observatory is watching. The James Webb Space Telescope is ready to look wherever astronomers point it. The outer solar system has been keeping its secrets since before Earth had a surface to stand on. The tools to read those secrets finally exist. The answer is coming. And whatever it turns out to be, it will change the story we tell about the place we come from.